The circuit we're looking at now in this problem is exactly the same circuit from the last couple of problems, but we're asking a different question. So we know when we reach steady state that we have a current through this inductor that is equal to E over R. And we know that the form of the current from the previous problem, just go ahead and put that in, the form of the current as a function of time is going to be the E over R onto E to the minus T over tau sub L, right? And by now you know tau sub L is the characteristic time constant for the circuit, and it's just L over R, and that works out to be seconds, right? Henry is an ohm second divided by an ohm gives us a second. So we now know the current in this resistor on the right-hand side as a function of time, and we're asked how much energy is dissipated in this as this inductor completely winds down. Well, power is a function of time. Right, is going to be P of T is I squared R. So that's what we see up here, I squared R. Oh, did not mean to click up there. I squared T. So that's just the power, right? And if we want to look at what energy is dissipated at any given little bitty bit of time, well, P dt, or I squared R dt, is energy, and so we're just going to sum up all the energy dissipated over all of time, right? So we have this U is the integral from 0 to infinity of this I squared of T R dt. All right? So this is just adding up all the energy dissipated over time to see how much energy is dissipated in this resistor as a function of time. Well, we know I, and so I squared, so we've got, we can pull out front, U is script E squared over R, because one of the R's cancels out, right? An integral from 0 to infinity of E to the minus T over tau sub L, right? Now all of that all of this, we have to square. All right? Okay. Didn't end up being the prettiest equation. There we go. Okay, so we're going to integrate this from 0 to infinity, and we've got e to the minus t over tau squared dt. You know, and we square that exponential, then it's really, it just becomes e to the minus 2t over tau sub L dt. And you know that if you have any exponential of the form e to the alpha t and you integrate it, you just get 1 over alpha. So 1 over alpha, alpha in this case is minus 2t over tau sub L, and we're going to get minus tau sub L over 2. So we've got this is going to be equal to squared over r, right? And onto a minus tau sub L over 2, and then we've got e to the minus 2t over tau sub L evaluated at infinity, which is going to be 0, right? E to the minus 2 infinity over tau sub L, that's going to end up being 0, minus e to the minus 2 times 0, which is going to end up being 1, right? So we've got here 0 minus 1. I'll just go ahead and type it in. E to the minus 2 times 0 over tau sub L, right? And so this ends up being 0 minus 1, which just gives us a minus sign, which just cancels out the minus sign on the minus tau over L. And so we end up with script e squared over r times 1/2 times tau sub L, which is L over r. And this just gives us script e squared over r squared L times 1/2, right? I'm going to rearrange this a little bit and put 1/2 L okay, not quite like that. It's frustrating with Microsoft when it decides to do things different from what I want them to do. Okay, and what is E over R, right? E over R is the current at time t equals 0, right? So 1/2 L I squared is what we have here, where that's the current at time t equals 0, which is just the energy that was stored in the inductor before we started. So all we've learned is we start out with energy stored in the inductor. Over time, all that energy gets dissipated in the resistor. If we add up all the energy that gets dissipated in the resistor, it's exactly the same as the energy that was stored in the inductor to begin with. And that's it for this problem.